Today I'm very excited to talk to you about the architectural choices you can make for multimodal models. And actually, it's one of the topics I've been working on. Without further ado, so I will first introduce the general architecture of transformer. And then I will move on to the architectural choices you can make for bridging multimodalities. And then I will show some evaluation results of one of the multimodal models called Lynx. And before that, I think from Tom's presentation last week, I think showing some disclaimers is always good. So I think so this is just a non-exclusive overview and with some personal opinions. So if you don't like it, please tell me and we can discuss further. Okay. So for transformer architectures, we know that we have encoder-only, decoder-only. Somebody also call it, language model. I think it's a bad naming because they can all be language models. And also we have the decoder-encoder model, which is the traditional sequence-to-sequence model. And this is the breakdown of the original transformer architecture. So we have the encoder layer, and then we have the decoder tower. And there has been a war, right, between all kinds of models and which one is the better. So we have, so this is an evolutionary tree. I find it very interesting. So at the bottom, we have, birds, I don't know, Elmo, those, very old traditional models. And we have 3 branches, right? We have encoder-only, encoder-decoder, and decoder-only. And what we can observe is that before GPT, right? Before GPT, Decoder-only was not as popular as, say, encoder-decoder models, right? And encoder-only model was really popular because of birds. But after the introduction of GPT-3, so as of 2021, you can see there's a bloom of models. There are a whole bunch of models, decoder-only models appeared after 2021, and this really thanks to like the efforts from OpenAI. They have been very determined to push in this direction. But also we can see that there are still models from this branch, right? Encoder, decoder models. And primarily, I think that's also because lots of those models are open source, like Flan, T5, and so on. And there's another trend is that we can see like many like this large language models are moving towards closed sourcing. Right? Previously, we have lots of open source models, but now you can see there are lots of moving towards those closed source model. And now we have this API oriented services from those leading clouds.
What's going on with encoder-only ones? Like, there have been any new ones since 2020?
That's a great question. I will touch upon that later.
Okay. So one question. Here, open source means that you can see the source, but it doesn't refer to the license. That maybe you can use that source really to do whatever you want, right?
That's a great question. Yes. So some open source license have a lot more restrictions. But for those truly open source, like MIT or like BSD3 process, those are allowing both commercial use and personal use.
Yes. So in this context, open source means just that you can see it or that you can also use it?
I think in this context, see if you can see BARD, GPT-4, I think it is that you can see the source code. If you can't see the source code like those BARDs and GPT-4, then
but like LLaMA is.
I mean, LLaMA, yeah, exactly. LLaMA is labeled as open source, so I mean, it just says it's
you can see the source
available somehow.
Yeah,
not necessarily.
Yeah, like literally open source, but
exactly.
Maybe
not philosophical.
it's not that strict open source that you can use to whatever purpose.
But I mean, even the term open source doesn't say that, right? So open source can be quite restrictive, like you don't know.
Yeah, it depends on who says it.
Yes, exactly.
Who understands.
Yeah, so coming back to Eric's question. So BERT, so let's first talk about the encoder-only models, right? Those very old traditional ones. So BERT stands for like bidirectional encoder representations from transformers. I'd like to highlight the directionality because it really allows information to flow in both directions, and so it's also one of the first foundation models for languages, NLP tasks, and it's the pre-training objectives are two, right? We are using mask language modeling and also next sentence prediction. And this really sparks a whole family of BERT models, right? For example, this BERT will have faster training, less memory cost, but also this comes with some performance derogation. Next, we also have a Roberta. So in this way, they throw away the next sentence prediction in pre-training, and they trained a lot more data for a longer time, and they achieve better performance. And actually, on the blue benchmark or blue benchmark, they achieved a lot higher performance just by simply changing the pre-training objective and train longer onboarding, which was very exciting. And also, we have a bunch more, right? We have XLM. It achieves great performance on cross-language tasks and for machine translation. Sorry, MT stands for machine translation. And we will also have a lot more like Roberta, Albert, and Liberta, and so on. But there are pros and cons for encoder-only model, right? So encoder-only model really gives great latent representation for our token embeddings, right? For example, it can like we always fine-tune models on top of those encoder models, and we do this for transfer learning. For example, named entity recognition, classification, sentiment analysis. But the thing is, one of the reasons I think it hasn't flourished so much is because they on their own is just an encoder. It's like producing great latent representation, but they themselves don't do much without further fine-tuning and adding additional prediction heads and so on. Next, we move on to encoder-decoder models. So this stream of models really stems from the sequence-to-sequence models, right? So we have the encoder, where we feed the tokens into, so in this case, traditionally we have those RNN or GRUs. Then we propagate the hidden states, one token at a time. For LSTMs, we probably will also have the hidden context. And then for decoding, we will just pass the last hidden states to the decoder, and also the start, like the BOS token to the decoder, telling it, saying that, okay, you can start decoding. And so for transformers, what we do is that we just replace the encoder with a transformer power, right? So the whole thing is fed like in parallel because we have the positional encoding. So everything is trained in parallel as well. So we have awesome speed, and also we have lots of models stemmed from the original 17 transformer model like T5, Flamingo, BART, Switch transformer, Big Bird. That's some of the models that we've talked about in previous sessions as well. But encoder-decoder models also have their pros and cons, right? So we have, as you said, we have two towers, and we have an explicit process of encoding the tokens. So this is good, right? We have it's being widely used for machine translation, summarization, and so on. And people have found that it's really good for fine tuning because we can train on multiple objectives. We can, get rid of some tokens and predict those tokens to fine tune our models. But it's really have a separate optimization space, and this being criticized in prior work. And for example, in perceivers, they really are trying to make an encoder and decoder fused into one tower, so you can optimize in one space. And actually, it's non-trivial to train practice because if I want to say I want to get the log probability of the whole sequence, and if but this is really hard to get if we train with like masked language models. Because the objective is binary, and also this was one of the observations from the CM3 paper. They said that it's empirically harder to prompt in practice compared to the Deck-only model, which we will talk about later. And actually, in practice, I also experienced that maybe not cross-attention, but decoder. Encoder-decoder models with those cross-attention blocks in between are harder to prompt. Next, we move on to Deck-only model. So for decoder-only models, or we call it Deck-only models, they were mostly driven by OpenAI, as I said, and they are unidirectional, meaning that the information only flow from left to right. So it's autoregressive in nature, and they are nothing but next token predictions conditioned on the previous tokens and the previously generated tokens. And we can train this in parallel because teacher forcing, right? We don't need to wait for the previous token to be generated. But this also introduces some biases into our training because during inference, if you have something wrong at the beginning, then you need to have some self-correction. But this is really hard to learn during the training process if you were to use this teacher forcing. And it's still a slow generation process because the tokens here are still generated one after another. So if you use inference, for example, the inference runner from Hugging Face, then there will be a for loop doing this generation. Then this really sparks a whole GPT family model, right? We have GPT-2, 3, 4 from OpenAI, and we also have Lambda, Palm, Bard we talked about previously, and Chinchilla from DeepMind, OPT, LLaMA from Meta, and also Lynx, which is a decoder model we'll talk about later. And this is a depiction of a decoder-only model where we have first a few so-called prefixes. So this prefix is the first few tokens of the sequence, and you fed into the model, and you predict the rest of them. And if you give, if the labels are given, then we have the labels. If are not, then the labels basically are the sequence that we fed shift to one place to the right. And decoder-only models are not without pros and cons, of course. So they are, autoregressive in nature. So it's great for generation task. And also a single tower architecture really helps with this coherent optimization space. It's much easier to train, practice, and also it's easier for prompting, and we can have different very flexible data format because we can interleave images and text into those prefixes and feed into the model. But the cons here would be that we don't have a very clear distinction between the prompts and the text. Sorry for coming back. For example, I want to insert a question here. Then we don't know which part is strictly speaking the input and which part is the prompt we're providing. And this could lead to some problems like linking prompts and so on. And also, it could be more resource intensive because we have longer sequence, and then in transformers, the longer the sequence, we will incur some quadratic compute and memory overhead.
Just a quick question, because I'm not so familiar with this model. So the prompt is essentially just what you prepend to the input token, so it's just another set of input tokens.
Yeah, that's true. That's true. So if say if you have an image text pair, then but the task will be VQA. So like very question answering, then you might want to append to the caption that you will that will be fed into the model. Say, you know, give me a short answer only, and that will be a prompt. So yeah.
Okay. Nice.
And we'll also come back to this technique because when bridging different modalities, people actually use this so-called prefix tuning, prompt tuning to bridge different modalities. Here, I'd like to introduce one case study between BLIP-2 and InstructBLIP, because I find it's interesting. In the paper, they implemented both decoder-only model and encoder-decoder architecture. So in this case, the BLIP-2 is using OPT and Flam5. So OPT is a decoder-only model. Flam5 is a encoder-decoder model, and InstructBLIP is using Vicuna as the OPT alternative. So as we can see here, so we have image encoded frozen, and the feature, so images are fed into the image encoder, and then it's being distilled to latent representation and being fed to the Q-former. And so Q-former is basically a bridge between the image encoder and the language model decoder, and then the Q-former will fed the learnable queries. So if you can recall, so that these queries are akin to what we've talked about in perceiver, those latent representations. So basically, after feeding those queries, they will be learned and extracts ideally some information from the image and fed to the decoder. And in this case, so the OPT model will be the top one, and the Flam5 will be the bottom. And this, so two observations I'd like to highlight here. So one is that images are never in direct contact with the text tokens. So you can see the role of Q-former is to indirectly mix in whatever it wants from the image into the latent learned query. So it's never directly interact with the text token. So ideally, the task of Q-former is to learn which information the decoder would need and extract them into the latent query and feed into the decoder. And one of the reasons why I highlighted encoder is because it's funny, because I felt that, you know, we were having two encoders, one image encoder, one image text encoder for the encoder-decoder model. Let's move on to the results. So here is the results, for VQA, and we can see in this case for InstructBLIP, they also scaled up like both Flam5 and Vicuna. In this case, we can see the results were quite on par between those two architectures.
So Flam5 XSL is 11 billion parameters, right? So actually Vicuna is smaller.
Yeah, in this case, Vicuna is smaller. Yeah. Yeah.
So, I mean, actually, this is a discussion topic because I don't have an answer. But like, whenever I read through these results from the BLIP-2 papers and InstructBLIP papers, and I mean, actually, I think the BLIP-2 line of work is really interesting because they do use multiple LM decoders, right?
Yeah.
And they are very different, like Flam5 XL and Vicuna 7 billion, which they do a report on in the same work, are very different, right? So like in architecture, pre-training objective, size. And my takeaway from reading their papers was always like, yeah, okay, bigger models are better. But it's actually not very much.
No.
Like, I mean, also from the VQA fine-tuning results, I was surprised how similar, for example, or maybe it's not that surprising, but the T5XL and the T5XXL was always very close.
Yeah. Yeah.
I don't know if anyone has some thoughts on this. Like, it's just I feel it wasn't very clear that one was like clearly better than the other, right? It was like always, you know, yeah, similar, close.
Okay.
But
I feel those models. Sorry. Yeah. Sorry,
no, go ahead, go ahead, Hongyu.
Yeah, I just wanted to come on that point. I felt that firstly, those models are vastly undertrained. So maybe they should have been trained on more data for longer. Maybe we can see the results. And secondly, yeah, I totally agree. I always confused when looking at the results because I don't know whether it's the problem of the data or the problem of the architecture or the model they use. So I think, yeah, but I mean, I understand no one has the financial results for ablation study that's detailed, like to peel apart every single component. Sorry, JP, you were saying?
No, I was saying those academic benchmarks are just like one perspective of the problem because usually I mean I think now in the team we have like a better understanding of on how those metrics are being calculated, and this is a far cry from like using human judgment or like GPT-4 as a judge. So yeah, maybe there is not that much difference between Flan T5XL and Flan T5XXL, but when we play with those models, I could still see some kind of like improvement and differences between both models, but we couldn't quantify them like I would say super well. So yeah, I'm just saying we should take that with a grain of salt. This is just like academic benchmark, and we know that you have like many biases in how those metrics are being computed.
Yeah. Great point. Thanks, JP.
Isn't that inherently problematic then also to your own work, Hongyu, in the sense of if we're saying, well, okay, VQA numbers and captioning numbers are just not able to capture the qualitative differences from even very different models, right? Going from a like XL to XXL is like a 5x difference in size. But then we're going to use it to see which modality encoders are better. Are we just, I mean, in one sense, we're saying like, oh, well, even giant differences, right, won't show up in the metrics. And the other sentence, we're saying like, but let's use the same metrics. Isn't there a big gap then in terms of getting a good signal?
Yeah, I think that's a fair question. So from my experience, especially from the last session, like the decoding methods, you can see it's really problematic to use those automatic metrics to evaluate the multimodal models. And you don't see a strong correlation between the model quality, like the experience you interact with the model, and the scores you show on those leaderboards. So yeah, I think maybe here human judgment will still be one of the gold standards to evaluate multimodal.
Okay. Yeah, I'm curious where you're going with this because I feel like so far we've looked at numbers and then we said, well, we can't take anything from those numbers.
Okay. Next, I will talk about some architectural choices for modality bridging, and there will be more discussions, I hope. So the first choice we can do is to do cross attention, right? So what does cross attention do? So in my opinion, so in my lingo, cross attention is refining the representation of one modality conditioned on another. So in this case, say we have images, we have text, and we use cross attention to refine the text embedding using the image tokens. So in this case, queries Q would be the target modality, and K and V would be the conditional information. And I always hated Sorry about this, but I always hated the Q key, query key and the value because it confused me a lot when I first wanted to learn this. So, but in my lingo, the Q is the quest. Okay, so this is the thing that we want to get out of from the transformer. The key is the key ingredients by which we want to mix in with the quest, and we want to calculate how much we want to mix with those key ingredients. And the value is the value that we want to mix in. So first we want to calculate like the dot product between Q and P, Q and K, and this computes the mixing ratios between the quest and the keys. So in this case, we have P and Q, and we compute the scores. So take this rightmost corner. For example, this would be how much we should mix our query with the value here. Sorry, with the first key here. And then we produce the refined version of our query. Then we see, okay, then how much we should mix our query vector with the second key that we are attending to. And this is the attention score that represents this. So basically, the final representation will be a weighted average using the two score of the computed from the key with the value vectors here. So we take the ratios and we using them to do a weighted average of the value and compute the final representation. So in this case, the query, the dimension of the results output would be the same as the queries, because the query, remember, is the quest, the target output. And the K and V would be the conditional information. So say this would be, for example, the text tokens, and the K and V generally would be the image tokens. And what we are doing is that we want to refine the text tokens condition on the information that we can extract from the V and Q. And we refine the information of the text or the captions, if you like. Yeah, so one example, so I will show a bunch of examples, how it's used in practice is Florence. Florence is a language multimodal. So as you can see here, we have Robota as the language encoder and Florence code Spring as the image encoder. And here, as we have, as I have said, at the top, if you want to know what the output modality is, you just look at the query. So in this case, the query is what is the language. So at the top, what we are outputting is the text tokens, refined text tokens. And at the bottom, what we are doing, we can see that the query is from the vision language encoder, sorry, the vision encoder. So the output modality here would be the refined image tokens. So that's, in this case, we can achieve the image text matching and mask language modeling, both objectives. The next example is the famous Flamingo paper. Right? In this case, we can also see a cross attention here. So what's above cross attention is frozen, but the cross attention is used here to fuse the language tokens and the image tokens. The image input here is still P and V, as you can see here, it's a bit small. And the language input as a query, because eventually what we want to get out of the model is the language text. So we will have text-to-text language models. And yeah, one thing I'd like to highlight here is that maybe you can see, if you can recall, the order between the self-attention and the cross-attention here is reversed in Flamingo. And I was a bit confused why it's the case, because typically what we have is we have self-attention, and on top of self-attention, we have cross-attention. But here, I think it's a design choice. Potential reasons could be the information flow, for example, because we want first mixing the image tokens. We want to refine our text tokens with the image information first. then we do the self-attention where we allow each token to attend to every other tokens. Another potential reason could be cheaper resources because cross-attention is typically cheaper than self-attention because we have another modality. We don't have the quadratic complexity here. But that's my educated guess. So take it with a grain of salt.
So they don't provide reasons in the paper why they do it in this order?
No, I don't think they've said anything about it.
And also no empirical investigation for whether this is better empirical?
No.
Okay.
Yeah, so if you look at the BLIP-1 and 2 paper, you can see first the self-attention, right? Always self-attention, then cross-attention. I think this is the typical setup. So in BLIP-1, what we have an image encoder as always, and we fit in, following the arrows, fit in the image information through cross-attention to the language model. So the text tokens come from the bottom, and then it's mixed in with the cross-attention as well. So this is the same for BLIP-2 as I've shown before. Oops, sorry. So here in the Q format, so the bridge, this figure basically is an enlarged version of the previous image. So here we have the cross-attention, the latent query fit in, and then we mix in with the image tokens as the key and values, remember? And then what we get out of is the latent representation mixed in with image information. Here is not the text token, but the latent representation. Another example is CoCa, which we heavily use at Apple. Here, what you can see is that we have an image encoder and a unimodal text decoder. And so I think this is basically an encoder. But anyway, they call it unimodal text decoder. And then we have the cross-attention where two modalities meet. So one thing I'd like to highlight here, they are using attention pooling. The reason for that is because we have different dimensions here. So in order to do cross-attention, we need, say, 256 tokens. But for the contrastive loss, in their case, they use one token only. So to do this, what you can do is to do something called attention pooling, basically a single transformer layer that changes, that projects one, one dimension to another dimension to bridge the dimension gap. So another method is decoder prompt tuning. I'd like to call it. So this is where we add different modality, the data of different modality to the prompt and produce auto-regressively the output. So this is one of the oldest methods and is more straightforward than cross-attention, I would say. And this originated from the control tokens from the encoder-decoder model. So for example, say if we want to translate English to Japanese, then we can add some specific control tokens at the prompt to indicate what kind of task we are doing. But for encoder-decoder models, it's harder to control compared to decoder-only model. And let me see. Yes, and one thing I'd like to draw differences here is that in literature, prefix tuning and prompt tuning are often mixed. But I think prefix tuning is quite different techniques where it's much more in-depth. So in this case, prompt tuning, we're only adding a short prompt in front, prepending a short prompt to our inputs. But for prefix tuning, we're actually changing multiple layers at a time. So quickly flush through some examples. For example, for Frozen, we have talked about in previous sessions. So Frozen, it features few-shot learning because we can fit multiple inputs as prefixes and get something auto-regressively as outputs. And then we have Fromage. So this is a very interesting paper. So it features in-context, the text got cut off, sorry, in-context image retrieval. There is image retrieval here. So basically they insert the retrieval tag into the prompts, and they can get some a feature vector out of it, and they do a similarity search. And this kind of a quasi multimodal output, I have to say. And then what we have is LLaVA. So LLaVA projects, so LLaVA is quite interesting. They bridge image and text modality just via a single linear projection. So they project the image tokens directly into the text space. And another example would be Oscar. This is a quite old an example. It's even older than Frozen. So what's interesting here is that if we have a dog sitting on a sofa or couch, and then because those two objects are overlapped, what they are arguing is that in the semantic space, the image regions are overlapped, but in the semantic text space, they are quite distinct. So what they are doing is that they are trying to use some special tokens and mixing modality to separate the space if they are overlapped in the vision space. And the third method to bridge is using adapters. So this is where like prefix tuning comes in. So in this case, we're not only adding some prompts at the bottom layer for the inputs, but also we're actively inserting some trainable layers in between. So in this case, in the example, we have the LLaMA-adapter. There are multiple other adapters. So as an example here, what we have is that they insert some trainable tokens only at the top for the top layers, because typically we have those bottom layers extracting very detailed features. We don't want to touch that, but we want to change some high-level semantics at the top layer. And also what they are doing is they are using two separate softmax. So in previous like BLIP adapters and so on, they are using a single softmax at the bottom to how do I say, to fuse the text and image tokens. But here they are using two softmax to separate the attention scores, which I found very interesting, and also they achieve higher scores as well. And also they use zero initialized attention gating to prevent catastrophic forgetting. Of course, there are also other bridging methods. I wouldn't touch upon that. So for example, there's a thing called multiway transformers, if you like. So basically they are splitting the projection or feed-forward layer to multiple experts, if you like. But I think we don't have the time for that. So if you are interested, please look into that as well. Here's a case study. I think it's quite interesting. One of the star models, I have to say, is called Lynx. So it's a kind of a mix between a Decoder-only model and an adapter. What they're doing is that they're using the Decoder-only model, but also they are inserting one adapter layer alternatingly between this frozen layer and an adapter layer. But nothing special after that. Everything is quite traditional. If we look at the results, so we can see it's quite surprising when I look at the leaderboard. So you can see Lynx for lots of talks, they are at the top of the leaderboard, but for some talks, for example, text translation is at the bottom of the leaderboard. And one interesting thing I'd like to talk about is their ablation study between cross-attention and Decoder-only model. So they also implemented a variant where they adapted to the cross-attention model, but also consequently, as Peter has kind of pointed out, they also dropped some data sets. So, so I don't think it's very conclusive, but they've shown that when using cross-attention, the performance dropped greatly. And what they argue is that, so on the right-hand side is the human evaluation. You can see the CA is the cross-attention, And PT is the deck-only, decoder-only architecture. And here you can see the decoder-only architecture performs a lot better. But I think it's problematic in the sense that they are using different training data. So that comes to my final slides. So if you have to remember something, I introduced several architectures, general architectures, like encoder-decoder models. And also decoder-only models are blooming nowadays for several reasons we've touched upon. And there are various architectural choices for bridging modality, like cross-attention, decoder, prompting, adapters. But which one is better is still up in the air. It's still an open question. So that's what I'd like to discuss today. And yeah, thanks very much.